Hello again. Thanks for joining us. This is a Q&A edition of Space Nuts. We talk astronomy, space science, and answer audience questions. Well, maybe we won't do one of those three things today. I don't know. We'll see how it goes. We've got a lot of questions to get through today. Fred reckons some of these are very, very tricky, so we'll see how it all pans out. A question about the expanding universe. Never had one of those before. A question about gravitons. Never had one of those before. Yes, we have. Photons and weight shift. That's all coming up on this edition of Space Nuts.
15 seconds. Guidance is internal. 10, 9. Ignition sequence start.
Space Nuts.
5, 4, 3, 2.
1, 2, 3, 4, 5, 5, 4, 3, 2, 1.
Space Nuts.
Astronauts report it feels good.
And joining us once more to unravel all of that, or maybe ravel it up even more, is Professor Fred Watson, astronomer at large. Hello, Fred.
Hello, Andrew. I do feel pretty ravelled at the moment, yeah.
Yeah, look, we have got some tricky questions. But before we get to those, we've received a note from Rennie in California. Rennie quite regularly sends questions in to us, but he sent us a really lovely note, which I want to share. He says, no questions today, just a thank you. I try to absorb as much information as I can listening to your podcast, and when I'm engaged in a conversation with my two grandsons, aged 15 and 12, I try to excite them and get them to think about our place in the universe and how it behaves. Now it's paying off with the announcement that my older grandson wants to carry on in college with some form of education in astronomy or particle physics. Thank you for paying it forward. Rennie. Isn't that lovely?
Yeah, it's great. Absolutely great.
I love it when we get feedback from people that become inspired despite us. No, I mean, it's fantastic. I'm really, really pleased. Really pleased. So pass on our regards, Rennie, to your boys or your grandsons and wish them well. And yeah, look, just I do the same thing with my grandson and three granddaughters. I talk to them whenever there's something interesting to talk about, and there usually is in the astronomical world. And I show them the images I take with the telescope, and I've even had them outside looking up at the moon. And it's captivating once they once you can convince them to actually get outside. The universe is their oyster.
Mm.
It's good stuff. So lovely to hear from you, Rennie, and that is really fabulous news. Are you ready for your first question, Fred?
Well, after a build-up like that, I guess we've got to tackle them, haven't we?
We probably should.
You're right. In a way, the ultimate mission of Space Nuts, I guess, is to provide that little bit of perhaps inspiration that might lead people to do things that might one day change the world. Who knows?
Yep, you just don't know. You just don't know. Maybe that's our lot in life, is to just try to inspire just a handful of people to pick up the baton, Fred. Who knows? All right, question one. It's like a test, isn't it? Question one. If space is expanding faster than the speed of light, then in millions or billions of years from now, will our night sky be completely black or a completely black void, or completely black, devoid of all light except our local solar system? That comes from Clint. This is something that has come up occasionally, and I think even in one of our most recent episodes, we were talking about the expansion of the universe and its significance, and I think in our Q&A episode, someone asked about the expansion of the universe. So here it is again. We are expanding, and it's expanding at an accelerating rate, although it's debatable whether or not that acceleration is actually as significant as it was. That is a separate debate. But I think it's pretty clear that in the long distant future of this universe, it will become a black void, won't it?
It's yes. So the answer to Clint's question is yes.
Okay. Question two. No.
No, exactly as you said. If you've got so when you say the universe is expanding at more than the speed of light, you've got to be a bit specific, because really what you're talking about is objects within the universe, which are being carried along by the expansion of the universe.
Yeah.
And so there will be, at a certain distance from us now, objects whose what we call the recession velocity is faster than the speed of light. But they're beyond the wall that we can't see beyond anyway, which is the cosmic microwave background radiation. But you can imagine as the expansion continues to accelerate, and you're right, it is still thought to be accelerating. We just don't quite know whether that acceleration is a constant. That's the thing you were alluding to, because there's some evidence that maybe the acceleration is reducing. But nevertheless, it's still accelerating, so it's still getting bigger, faster all the time. And so what that would do, you can sort of imagine in your head what this situation would lead to. It means that the sort of black horizon, the horizon which is where light can never get to you because it's being carried away, the objects are being carried away faster than the speed of light, that black horizon will approach. It'll get nearer as the universe's expansion continues to accelerate. So eventually you can imagine that maybe you would see just the other galaxies in the local group, which is Andromeda and the Triangular, the Whirlpool galaxy and things like that. But eventually, it might just be objects in our own solar system, which makes astronomy a little bit of a boring game. Yeah.
Well, let's go see what we can find. Oh, there's the moon.
Yeah. Oh, wait, it's gone.
Well, it's moving away from us too. So
it is rather slower than the speed of light.
Yeah.
6 centimetres a year, I think.
I can't imagine this is going to happen in an awful hurry, Fred.
No, it's not. It's very, very long way down the track. And of course, from our perspective here on Earth, long before anything like that takes place, we'll have been confronted by the expansion of the sun itself as it turns into a red giant star.
Yeah. Who knows where we'll be in the universe by then. We might have moved out into other parts of the galaxy by then if we've managed to find some kind of propulsion system or learn how to fold space or whatever it is you need to do. Maybe develop wormholes and be able to travel mega distances fast.
Well, you're the person, you're the science fiction writer. You've got to tell us what it is we're going to do.
I'm working on warp travel at the moment.
Oh, good.
In my novels. So I'm doing the final editing at this stage, and it's the most horrible job.
It is, isn't it? Yeah.
Especially the writing's fun.
Yeah.
But then you've got to fix all your blunders, and you don't realise how really hopeless you are until you have to edit
your own stuff.
Yeah. Yeah. I'd pay someone, but I can't afford it. It's not a cheap thing to get done, book editing. But anyway, so the basic answer to Clint's question is yes, it's going to happen. There will be complete black nothingness in a matter of about 3 weeks' time, or could be 3 gazillion years' time.
Yeah, I think the latter's more likely.
More likely the latter. Thank you, Clint. Great to hear from you. Our next question comes from somebody whose name I forgot to write down. No, it didn't. It comes from Alan. Now, this is a pretty big question, so I'll just go straight through it and we can figure all out the rest out later. I know you want audio questions, but you know how they say you have a face made for radio? I've got one of those. Well, I have a voice made for text. That's very good. I hope it's not true. I discovered Space Nuts more than a year ago and have listened to your entire back catalogue. Wow. Get a job. No, fantastic. Thank you. Still listening and have not lost my mind yet. Wow, that's a record. Here's something that's been bothering me for some months. Some physicists don't believe relativity when it says that gravity is not a force. Also, they believe that all forces are conveyed by particles. To unify gravity with other forces, they postulate the graviton to be that particle for gravity. It's said that nothing escapes a black hole, but actually gravity does. If gravitons exist and convey the force of gravity, then they escape black holes, so they are not affected by gravity. That means they do not affect each other. We know gravity does affect all massive particles and photons, massless particles that convey the electromagnetic force. I don't know if gravitons affect other massless particles. This is the interesting part. If F equals gm1m2 divided by d squared is the complete calculation for the force of gravity, no modifications introduced by relativity or quantum physics, then gravitons are not affected by anything. So gravitons affect every particle except gravitons and are not affected by anything. So is an asymmetry that breaks conservation of energy and momentum. My question is, here it is, why do some physicists still believe in gravitons? That comes from Alan in San Antonio, Texas. Boy, Alan, you've put a lot of thought into that. You really have.
Yeah, and these are questions that are right on the money as well.
Yeah.
Especially the last one. Why do physicists believe in gravitons? I think most physicists probably do, Alan, because we know that gravity is a fundamental force, and all the other fundamental forces have their subatomic particles, which are basically particles that what we call them bosons. They carry a field in a way, and the field is another way of looking at how a force works. I didn't phrase that very well, but that's why some physicists believe in gravitons. We've never found them. We don't have a particle physics theory of gravity, so we don't know that they exist, but I think most physicists would assume that they exist. And so that first conundrum that you mentioned, if nothing escapes a black hole, well, gravity does. And so if gravitons exist and convey the force of gravity, then they escape black holes. So they're not affected by gravity. That means they do not affect each other. But in fact, the bottom line with black holes, it's quite complicated. But you don't have gravitons escaping from the black hole. The way people who know a lot more about these things than me, the way they envisage this is that the gravitational field of the black hole is a kind of fossilized one that was established before the collapse into a black hole. Or, and here's another way of looking at it, and this really, you're going to think, Alan, this is a cop-out, but this is the way the physicists see it. The gravitational field of a black hole basically includes something called virtual gravitons. Oh. And so that sort of ties in with the fact that the gravitational field is a fossilized footprint, if I can put it that way. The virtual gravitons are an embodiment of that, but they don't necessarily obey the normal laws of physics. So basically what you've got here, and I think the physicists who look at this problem probably just automatically drop into the two camps of relativists, people who are experts in general relativity. That's Einstein's theory of gravity that says, yes, gravity is not a force, it's just a distortion of space. And the quantum mechanics people who look at it from the perspective of gravitons. And so, the virtual particles, the quantum mechanics person's answer to this, they're basically just mathematical constructs in a quantum field. And so they don't have to obey speed limits or anything like that, or even don't have to worry about the event horizon. So they can continually basically keep the gravitational force there without actually being trapped by it. I think that's the way physicists look at it. It sounds...
all that says to me is it's something. It's still a big mystery. There are so many different theories behind gravity, and we really don't know what it is. We know what it is, but we don't know why it is.
Well, no. So all we know about gravity is the way it behaves. We really don't know what it is. And in a way, Alan's question is well posed, because it could end up that it's something different and there aren't gravitons. But that's why we haven't found them, because they're not there. It's fascinating. I mean, in a sense, it's gravitons are along the same line as the hypothetical dark matter particles. We know dark matter is real. We know it's there. We assume it's subatomic particles. We've seen some recent work that suggests perhaps they're not. Perhaps it's not subatomic particles, but primordial black holes, which can be very small and very difficult to detect, which takes us back to the macho theory, massive compact halo objects, the macho theory of dark matter, as distinct from the WIMP theory, the weakly interacting massive particles. So I think gravitons almost fall into the same boat as dark matter particles, in the sense that we haven't detected them. We hypothesize that they're there. We've built constructs like virtual gravitons that allow us to do that without going completely mad. But at the moment, still, I think the door is wide open for all kinds of new ideas that might change our view completely.
Yeah, I guess the day we crack it, we'll go, oh, yeah, I should have thought of that.
Exactly. Well, Alan's already thought of it.
Yeah.
In terms of what the conundrums are and why it's so difficult. Yeah, it's a great question.
I guess the question that comes from that is, does it have to be a particle? And the answer is no.
No.
It doesn't have to be, just because everything else is made of particles. So
yes, that's right. I mean, so what's called the standard model of subatomic particles is this group of 17 particles which we don't think can be broken down into anything smaller. That's why they're called fundamental. And they account, among them are the force particles, electromagnetic, strong and weak nuclear forces, which we know about. Gravity is just assumed to be a fundamental force with its fundamental particle, because it behaves in every other way. It behaves like the other ones do, but we just haven't managed to pinpoint the particle itself.
There you go, Alan. You've kind of put your thumb on one of the big mysteries of the universe and expected us to have an answer. No, it's just one of those great big question marks in space. If you look up, you can see a giant question mark in space, and that's gravity. But
yes, that's right.
Yeah, whether or not there are gravitons, the debate remains. Thank you, Alan, for the question. This is Space Nuts. Andrew Dunkley here with Professor Fred Watson.
I believe that this nation should commit itself to achieving the goal before this decade is out of landing a man on the moon and returning him safely to the Earth.
Space Nuts.
Fred, our next question comes from somebody else who's thinking particles. I spend a lot of time thinking about photons and have so many questions about them. I know this about Misty because she's always walking around with a light bulb above her head, so that explains that. Photons are really weird to understand. I'm curious to know if there are any fundamental particles that do not have a wave function. And then, is it possible to detect a particle or photon that does not have any properties of a wave? And the last part of the question, is it possible for a photon or particle to have such a long wavelength that we don't have a detector big enough to pick it up? That's from Misty in Pennsylvania, one of our administrators on the Facebook podcast group. So thank you, Misty, for sending in a question. Nice to hear from you. And beautiful part of the world, Pennsylvania. Got to drive through that last year, and it is absolutely lovely in summer. Don't think I want to be there in winter. Nevertheless. Okay, so photons. Yeah, what can we talk? What can you Tell us about, are there any particles that don't have wavelengths? That's an interesting question.
Yes, so that's more or less what it amounts to. So we see in quantum mechanics, we see this fundamental thing that particles display the properties both of a particle and a wave, and so we call it a wave function. And as I understand it, and I think quantum mechanics backs this up, there are no fundamental particles that don't have a wave function. So they all exhibit this wave-particle duality. It is, I guess, the way that particle physicists think about these things are a little bit different from the way we might interpret it. So when I think of the wave-particle duality, my mind immediately goes to the photon, which Misty's already mentioned. Yes, we understand photons as particles because we see the photoelectric effect, which insists that they've got to be particles because you get basically quantized amounts of energy out of them. But then when I think about the waves, I think about things like polarization, where you've got waves that are oscillating in different directions. I think we talked about that a couple of episodes ago.
We did.
In the mapping of the magnetic fields of the galaxy, of the universe. And so I always think about waves vibrating through a medium. But the physicists kind of combine those two ideas and think in terms of something, it's usually called quantized excitations of underlying fields. So that's to say that it kind of mixes both relativity and quantum physics here, because the underlying field is what it's the sort of, if I can put it that way, the background canvas on which the information is superimposed, and the particle is a bit of that background canvas that is excited to vibrate and give you a wave. But it's excited in a way that is quantized. That means there isn't an infinite number of different excitations that can be set up. They're specific numbers, which means you get specific wavelengths from the excitation. So it is all a mix of particles and waves, but it kind of brings it together. And once you think of it in those terms, then it becomes clear that you can't have a particle without its wave function. So
which kind of writes off her second question, if there's a long enough wavelength that we haven't got the equipment to detect it.
No, I don't think it does.
Okay.
Because I think, we in a way, the ultra low frequency radio waves are a bit like that, because they are, some of them have got a wavelength bigger than the Earth.
Oh, wow.
And so how do you detect that? Well, you've got to have a spacecraft that's got the other end of the aerial on it, that sort of thing. There's also, what was I going to say? We know that there are gravitational waves that have got wavelengths measured in light years. I think the gravitational properties of the Big Bang, so the gravitational waves that were set up by the Big Bang, are extremely long wavelength. I think I've got that the right way around. It's so, and we, there are ones that we don't have normal everyday ways of detecting them. There are subtleties because you expect some of these waves to be polarized, and that, I think, gives you an insight into it. But yeah, it's it is a good question, and I think once again, Misty's thinking outside the box. No particles without their wave function, because a particle is an excitation of the underlying field, a quantized excitation of the underlying field.
So it is possible we cannot detect certain wavelengths because they're too big, but they still exist.
I think that's right, yes.
Yeah. All right. What about gravitons? Do you reckon they'd have a wavelength?
Well, yes, they do. That's the thing.
If they exist.
Yes, because because we've got gravitational waves, so the wave-particle duality works both ways. If you've got a wave, you've got a particle.
There you go. Good one. Thanks, Misty. Hope all is well in Pennsylvania.
3, 2, 1.
Space nuts.
And our final question comes from another one of our regular contributors, Casey in Colorado. What does it feel like to go from weightlessness to normal gravity for astronauts when returning to Earth? I think it would depend on how long you've been up there and whether or not you've actually bothered to use the treadmill.
Well, that's right. The treadmill's all about keeping up your muscle strength.
Exactly. Because once you're out there, your muscles immediately start to wither.
They do, and you don't really have anything against which to push to keep them, keep them going, other than the torture equipment that they NASA and Roscosmos provide on their space stations.
I think on Space Lab they didn't have a treadmill; they had a running track that ran around the inside of wall of Skylab, I think. And so I've seen footage of astronauts actually running in a circle around the interior of Skylab.
So they're keeping themselves running just by the centrifugal force that they're setting up.
Yeah,
Yeah, that's interesting. I didn't know that. That's
I'm sure that if you look online, you'd find footage of it. I strongly remember that. I saw it on the news one day and thought, wow, how did they do that? Well, there's no gravity. Duh.
Yeah. Wasn't there something like that in 2001: A Space Odyssey? I think there was.
Could have been.
I think there was.
I watched that very recently. I just thought I really wanted to watch it again, but I fell asleep. But it's very late. Judy had gone to bed, and I thought, I might just start this. But I was gone. What was the question? What's it feel like? I also remember seeing footage of cosmonauts coming back from very long haul time in space, and they'd get them out of the capsule once they came back to Earth, and they couldn't stand up.
Couldn't stand up. Yeah, I've seen similar things, and even with the exercise that the Artemis II crew were doing, they were a little bit wobbly when they got out of the spacecraft, and we all saw them going across the deck of the recovery ship.
Yeah.
So I think how wobbly you are probably depends on just how much effort you've put into keeping up your muscle strength. So I think that's the key thing that Casey might be thinking of. Exactly as you've said, your muscles go to waste very quickly, and if you don't exercise, then you're going to be in big trouble. You would not be able to walk. So quite a significant thing, which would also, of course, depend on how long you've been in space, how long you've been weightless.
And the other thing they might suffer from is fatigue, because they have to work so much harder to achieve the same mobility as they were used to when they had full muscle strength.
Yes.
So they'd get very tired very fast.
Yeah.
I think, all jokes aside, I think the everyday person who's been through immunotherapy or some form of inhibitor for testosterone, for example, for cancer treatment or something like that. That has the same effect on your muscles, muscle wastage. When you stop producing testosterone as a male, your muscles actually do fade away, and you've got to do exercise to keep, like astronauts, you've got to keep your exercise up to keep your muscles in trim. But it does slow you down. And case in point, I did have that sort of treatment for my prostate cancer, and for 6 months I went into basically the equivalent to menopause. I had muscle wastage. I kept up my exercise, but it wasn't enough. And I had a situation where I'd go out and play golf. I lost 40 yards on shots simply because my muscles had wasted away. And it's probably taken a year to get it all back.
Yeah,
so,
interesting.
Yeah, it would be the same effect for an astronaut.
Yep.
Exactly the same.
Yep.
Different,
different mechanism. Yep.
Mechanism, but same effect. And the other thing that they'd probably have to deal with is some of them have very significant health effects from being in zero G, and you come back to Earth. Like we had wasn't there an astronaut recently who was temporarily blinded from zero G, and there's all sorts of things that they can suffer from. And a lot of the time when they come back to Earth, it does fix itself because you're back in your normal environment. But when you're out there orbiting or going to the moon and back, it is not a human environment. It's not normal.
Yeah, so it was an evacuation the beginning of the year, I think it was, that we only really found out a few snippets about not very long ago. And I can't remember what the details were because my brain's atrophied because of old age.
Yes, indeed. But there would be various levels of dysfunction as a consequence of spending time in space.
That's
it would
right.
be It would be a person-to-person variable. It's not a one-size-fits-all situation. Some people who'd come back probably not feel anything. But if you're up there long enough, it's going to have a big impact on you.
Yes, indeed.
Thank you so much for the question, Casey. I hope we covered it reasonably well. Anyway, in the not-too-distant future, I'm pretty sure there'll be so many people going in and out of space, they'll come up with ways of dealing with it. Who knows? And I think that brings us to the end. Don't forget, if you've got questions for us or observations or comments or whatever you like, you can go to our website and send it to us in a text or audio format at spacenuts.io or spacenuts.podcast.com, and just click on the little AMA button at the top. That stands for Ask Me Anything, and you can send it through. Don't forget to tell us who you are or where you're from. And Fred, that's it. Thanks so much for answering those. That was a tough batch today. Some of those.
Great questions, though. Well done to all our listeners for what they do in terms of thinking through a lot of these issues. It's great.
Very good. All right. We'll catch you real soon, Fred. Thanks so much.
Looking forward to it. Thanks, Andrew.
Professor Fred Watson, astronomer at large. And thanks to Hugh in the studio, who couldn't be with us today because there was so much going on with gravitons and weightlessness. He just decided to float away. And from me, Andrew Dunkley, thanks for your company. We'll catch you on the next episode of Space Nuts real soon. Bye-bye.
Space Nuts. You've been listening to the Space Nuts podcast.
Complete Houston.
Available at Apple Podcasts, Spotify, iHeartRadio, or your favorite podcast player. You can also stream on demand at Bytes.com.
This has been another quality podcast production from Bytes.com.